Chameleon's long, elastic tongues are one of the fastest muscles in the animal kingdom, extending more than twice their body length. Researchers found that the animal's tongues are capable of impressive acceleration, doing 0 kilometers to 100 kilometers per hour in 1/100th of a second, 10 milliseconds. What is the acceleration of the tongue? During a strike, the chameleon's tongue accelerates with the above acceleration for 10 milliseconds, then travels at a constant velocity for another 10 milliseconds. During the total time of 20 milliseconds, how far does the tongue reach? So let's start by converting some units, because we can't use kilometers per hour. We have to convert it to the standard unit of meters per second for velocity. So let's quickly do the conversions. 100 kilometers per hour times 1,000 meters per kilometer times 1 hour every 3,600 seconds. And now after the conversion, if you round it, you should get that 100 kilometers per hour is about 27.78 meters per second. And so I'm just going to use this value since this would be precise enough for now, I guess. So you can use the kinematic equation that the final velocity equals the initial velocity plus the acceleration times the time, since we have all of the variables we need except for the acceleration. And again, the initial velocity is 0 kilometers per hour, which translates to 0 meters per second. The final velocity is equal to what we just calculated, 27.78 meters per second. And the time interval is 10 milliseconds, which corresponds to 0.01 seconds. So now we have all of our things ready, and if we solve for acceleration, it's simply the final velocity divided by the time, since the initial velocity is 0, so we can just take that out of the equation. Now solving that, we can get that the acceleration is equal to 2,778 meters per second squared, which is a really fast acceleration. But it's like being applied for like 1/100th of a second. So if it was applied for 1 second, it'd probably accelerate to about like 5,000 miles an hour or something. So the acceleration is equal to 2,778 meters per second squared. And that's the first part. Now we need to calculate the second part, the total distance, or how far does the tongue reach. So we're given that it first accelerates for the first 10 milliseconds, for the first 100th of a second, and then travels at a constant velocity after being accelerated. So for the first part, we can simply use this kinematic equation, that the displacement is equal to the initial velocity times time plus 1/2 times acceleration times the time interval squared. Again, this part can be totally removed since in the first part it's still accelerating, so it has no initial velocity. So the change in x, or displacement, simply 1/2 times acceleration times time interval squared. So if you plug everything in, half times the crazy acceleration times the time interval squared, which reduces it down to a really ridiculously small amount, and you get that it is about 0.1389 meters, so about 10 centimeters. And then, that exactly 0.1389. And that is the first part. Now the second part, we can just simply use the same kinematic equation, just a different part. If you recall, the change in x is equal to the initial velocity times time plus 1/2 times acceleration times time squared. So during the second part, it travels at a constant velocity, so there's no acceleration in the second part. So we can get rid of that. And this initial velocity that it travels at is simply the final velocity after it stops accelerating from the first 10 milliseconds. So this velocity is simply what we calculated earlier to be as it goes from 0 kilometers to 100 kilometers per hour in 10 milliseconds, which when we convert it is about 27.78 meters per second. So that is the value we will use for velocity in this case. So in the second part of its motion, the displacement is simply the velocity after accelerating, 7.78 meters per second, times the time interval of 0.01, or 10 milliseconds again. And this will give you 0.2778 meters. So slightly more than when it's actually accelerating, since it's already moving at that high speed. And now all we need to do to get the total, to erase this one. So to get the total displacement of the ton, total, is simply equal to the two displacements from the two stages added together, since you have the displacement during the acceleration and the constant velocity. So we just simply add these two together. That becomes 0.1389 plus 0.2778. And this gives you the final displacement of 0.4167 meters. And I'm just not going to round this for now since it's only 4, but this is the displacement during the total time of 20 milliseconds. And that is how you would solve this problem here.